Okay, good afternoon, everyone. Thank you very much for coming this afternoon to hear about our project. As he said, my name is Ana Cavalcante. I'm the leader of the work package on foundations. And I think when I say this, perhaps many of these students, I know that there are some professionals at least online, but professionals online, I'm sorry, I'm going to talk to the lovely students that are here in front of me. And I think perhaps when you hear the word foundations, you say, oh no, here comes even more mathematics than what Claudio has just shown me. Not true, and I'll show you, I'm going to show you just pictures. And at the end of this talk, I'd like to have convinced you all that you want to be software engineers, and I want you to know what that means, okay? So I am the leader of this RoboStar, which is a center for software engineering for robotics, an international center with a presence across several countries. But my talk has a subtitle. And the subtitle is From Computers Says No to Robots Says Yes, Engineering a Positive Future for Robotics. This is a joke that only works in the UK, but I wanted to bring it to you anyway. There is a comedy show in the UK where there is an actor that plays the role of a banker, a receptionist, that when people come, the customers come to him and say, could I please do that? He looks at the computer and says, the computer says no. And people are not terribly pleased. But in this young audience, I know that you use computers all the time. Sometimes when I'm talking to older people, I have to convince them that they are using computers all the time. But I know that you are aware of. And I will absolutely ascertain with all certainty that computers have said no to you more than once. Computer says no when you are trying to type something and the screen freezes. It's saying a really big no to you. It says no when there is a bug and you have to find a way around. It says no when there is a bug and there is no way around, you need to wait for an upgrade. So it's saying no to you all the time. And we accept that. We actually accept that. It's partly our fault as a society. Robots are computers, but they have a body, right? We've been talking to you about robots, and we didn't tell you what a robot is. A robot has a body that can perceive the environment and can affect the environment. When a robot says no, there may be several concerns about safety, about many things. Safety is a problem that we tackle in RoboStar and in RoboSapiens. So we want to engineer a more positive future for robotics where robots do not say no to us. And what's going on? What is happening with these robots? Well, we've already been told, I believe it was Roland, that he said, well, one way in which robots can be safe is if we put them behind cages. And it used to be the case that robots were in factories behind cages all the time. But he's already mentioned that we want robots to be able to be closer to us. And what's changed in the recent years is that there have been advances in electronics, in mechanics, and artificial intelligence. I know that this audience will be very interested in artificial intelligence. That means that robots have evolved, they have extra facilities, and there is a lot of interest that they can be closer to us, right? Colleagues, I think we'll talk to you this afternoon, and I don't want to raise expectations. I think perhaps there are already too many. That's what one of the concerns we have in the project is that people think that robots can already do autonomously and much more than they can actually do, that they are much more intelligent than they actually are. And there is a hype in the media, and I don't want to add to that, but there are very good perspectives. The advance that we've made means that robotics can be really useful. Robots can be useful in space, in the deep sea where we cannot be. One of the RoboStar collaborators worked with us on applications for nuclear decommissioning, where we are developing robots that can help to clean the environment, go in nuclear contaminated environments where we cannot go. So they can be very helpful. But all these advances that we've seen mean that we can now have the perspective of these robots working close to us. Medical robots that can be much more precise than an actual doctor, than the hand of an actual doctor. You can have robots the perspective of having robots in offices, homes, hospitals. Another one of our case studies and one of the RoboSapiens partners is interested in robots in hospitals. Not to replace nurses and doctors, but to relieve them of menial tasks. These robots need to be interacting with the patients. We can think about robots working with our elderly. And again, in RoboStar, we have an application where we can have robots that help people that have cognitive or mobility impairments get dressed. We can have robots helping us with education of our children, entertainment of our children. But in all these applications, we want the robots next to us. They need to be safe. There is a word that I could spend the rest of the afternoon talking to you, which is trustworthiness. And there are so many aspects of trustworthiness. But I'd like to talk to you, of course, about the issues that are generated by software. Okay? And one thing that I'd like you to realize is that just like a bridge, just like a car or a building or a laptop, a software is an engineering artifact, right? And our society is very lax with this. If that's a beautiful bridge in New York where I work, if that bridge starts cracking or collapsing, we're going to go back to the civil engineer and say, what have you done? We will sue the company. We want something done about it. If we buy some software and it doesn't work, even if we pay good money for it, we say, there will be an upgrade. It's okay. That every engineer provides guarantees for their products, but software engineers do not. I understand that you are our students here, computer science students. Are you happy with that? When I was your age and I was studying, I wasn't happy with that. I started learning about programming and algorithms and so on. It all looked very intuitive. And I thought, what am I doing here? Even if I'm doing my exam, I can't be sure that my algorithm is going to be correct because I'm using my intuition. And then someone told me it doesn't need to be like that. We can have software engineering with capital E, where that E means that it is really an engineering discipline. And I'm really happy that with RoboStar and with RoboSapiens team, we are all working together to make that engineering a capital E. And what is needed for that? Well, we don't blame the engineers. We blame the tools. I will not blame the software engineers. You are wonderfully young, but if you could go and talk to your parents and ask them how the world was 40 or 50 years ago. The world absolutely changed in so many ways, in connectivity, in services, facilities, and at the center of that change is very successful software engineers. So I don't blame the engineers at all. However, the engineers, they need to use models. And our software engineers, they are not doing that. The software engineers for robotics, they are not doing that. And why do they not do that? Why do they think that they cannot do it, right? So let's think about the civil engineer again. I really like that example of the civil engineer. So you would never imagine that a civil engineer, for instance, the group that built this building here where we are now, we cannot imagine that on day 1 or 2, they started making holes on the floor and lay some bricks. But laying bricks is to civil engineering as programming is to software engineering. If you start your development by writing some code, that's what are you doing. The next time you start, you have a problem to solve, and you start thinking, let me write in some code, think, oh no, hold on, I am an engineer. And an engineer does not start laying bricks. We need models. Civil engineers use their models, and we'll know what they are, their plans, their maquettes that they use with tools to make sure that the building is not going to collapse, that all the services that we expect are going to be in place before anything is constructed. They can do that. And the really good news is that we can do the same thing for software. We have been using hearing the word models this afternoon lots of times. But what I'm talking about here now, they are engineering models. Okay, and what's the problem with this lack of specialized tools that support the roboticists to use these models? They start playing bricks. They start by writing some code. And they look at the problem of the software of the robot and say, oh, it's a bit of programming. We've seen some of that this afternoon. And what happens is, if the code is all they have, when they go and do that testing, which is extremely expensive, that's what they can do is to go and change the code if they find a problem during testing. And they go and change and test again and change and test again. And in the end, all they can say is, I could not find a problem. They cannot say, I am now happy for this robot to go into people's homes because I know that it's not going to misbehave. We are not there. For that, we need these models, okay? And so an engineer will need to use mathematical, software engineer will need to use mathematical models, just like any engineer does. The principles of programming are already known. They've been known for decades. Since the 60s and 70s, people found that out. The techniques that are based on these principles, they are called formal methods. With the advance of computers and the improvement of computational capacity, they are very much widely used in industry, right? So if you think about Microsoft, Meta, now the old Facebook, Amazon, they're all using these formal methods, okay? But roboticists are, by far and large, every generalization is a danger, not because they don't have these specialized models. The models I'm talking about are these recipes that describe the behavior of the robots. And are there any chefs in the audience? I'm not a chef, right? So it's my husband that cooks in my house. But I try every now and then, and I go to the recipes. And the recipes talk about cook until it's a little bit brown, or put a pinch of this, that, and the other. It's all very imprecise, and I need to go and find a domain expert, my husband, and ask what am I to do here? And sometimes I don't even realize that I should have asked the question. And here's what I get instead of the lovely cake that I wanted to do because of this imprecision. And so roboticists are in a bit of a similar situation. Instead of getting these perfect cakes, they are working with recipes that look like this. This is a set of, I'll call them diagrams, that comes out of a paper from a robotics journal. And it's not unique, it's from a friend, and he's not upset that I'm going to tell you this. This is not a model, this is a drawing. And I'll make the parallel if a civil engineer gets to your home and sketch something on a piece of paper. That is not a model, that is a drawing. It is a model at the moment that I can put it in a tool and start deducing some properties of it, making sure that there will be enough water flowing in the building. If I can say something about it, if I can use it to predict something, then it is a model. Otherwise, it is a drawing. And these things, I could not use that. I had to go and talk to my friend because I wanted to work on that example. So in RoboStar, with RoboSapiens, we are developing notations and tools that allows us to have diagrams like that. I don't need you to understand the details of any of these diagrams, right? I'm just showing you the difference between a drawing that you find in papers and a proper model. That model there was developed with the tools that we are using and further extending in RoboSapiens. It has a mathematical meaning, and therefore we can derive value from it. Using those models, we can obtain the guarantees that colleagues like Roland, like Claudio are after. So I have here a video of a part of our tool. Our tool has more than 3 million lines of code. It has the video started? Yes. Has been developed by colleagues in RoboStar across the world, and we are extending it here. What I show you here is the core element of this tool that is supporting the modeling of the software, and that can, because that model has a mathematical semantics and can help us to prove properties even before I have laid the first brick in my software, right? I can still prove that it has certain characteristics that are important for my application. I can also derive value from it in different ways. I can generate code. I can generate tests. Testing is extremely expensive. And being able to generate those tests and say with those tests what the verdict should be is extremely useful. So in this approach, what we have is model-based engineering. We start with the models. And what I have here in the end is a report that this tool provides relation to some properties that we decided are key for our application, and let's say if those properties hold or not. And if they don't, I can change the models, and that's much cheaper than changing the code once I've started doing it, right? So the idea, the future that we envisage, is that we can get consistent outcomes, really beautiful cakes, really trustworthy software robotic software, so that we can use these robots with confidence. In that context, we will be able to say, well, I can put my robots to look after the elderly, look after the ones that we love, look after the children, to be with them in our offices, in our homes, and so on. And if we are using those applications, then in this technique, then the robots will always be saying yes to us. And that's what we wanted. Thank you very much for your attention. I want you all to become software engineers. And here's some credits for the images. And I hope that you're excited enough that you go and follow us. This is the LinkedIn page for RoboStar. From there, you get to RoboSapiens as well. Thank you very much for your attention this afternoon.